In the last video, we introduced the ideal gas law that relates all four of the main gas variables: pressure, volume, moles, and temperature. And I mentioned that using the ideal gas law, we can derive the relationship between any two or three variables from this one equation. So in this video, our goal is to learn a little bit more about how we do that to be able to apply these types of relationships to various problems. So what we need to do, the word like derive an equation strikes fear in the hearts of many, but it's really not that bad. All we really need to do in order to figure out the relationship between any two or three variables is to rearrange this equation to put all of the variables that change on one side and all constants on the other. And what this allows us to do is that once you have put all of the constants on one side, what it means for like pressure times volume equals a constant is one of the relationships that we kind of already saw earlier, just based on our understanding of molecular movement, means that pressure times volume is going to be the same before and after you create some change to one of those things. So we can set pressure times volume initial equal to pressure times volume final before and after we've applied some change to this system. So I think this makes more sense when we see it in action. So we're going to do some examples. The first one we're going to take a look at is a balloon containing a sample of nitrogen, occupies a volume at 15 liters at 298 Kelvin. What volume will it occupy at 200 Kelvin, assuming pressure remains constant? Also, we're talking about the same sample, so it is implied that the number of moles is remaining constant as well. So we have two different temperatures given to us here. 298K and 200K, sort of before and after we've changed the temperature. And we're given a volume at 298 and asked what the volume will become at 200. So we're looking to relate the volume and the volume and temperature before and after the temperature changed. So the things that are changing our changing variables in this situation are the volume and the temperature. The things that are remaining constant are the pressure, the number of moles, and R, because R is always constant. So we want, in order to determine the relationship between volume and temperature, to start with the ideal gas law. And we want to put our changing variables, which were volume and temperature, on the same side of the equation, and then all of our constants on the other. So we need to get V and T on the same side of the equation. Easiest way to do that is going to be to divide by T, and then we need to get P over with N and R, so we can divide both sides by P. So V over T is equal to NR over P, just simple algebraic rearrangement of this equation. But because NR and P are all constants in this situation, what that is telling us is that the volume divided by the temperature is equal to a constant. So that means that the volume over the temperature at some initial point in time, let's call it time 1, is going to be equal to the volume divided by the temperature at some second point in time. Let's call it time 2. So this relationship of V divided by T equals a constant is allowing us to say that V divided by T at some point in time is going to be equal to V divided by T at some other point in time. And that's how we're able to approach this type of scenario without specifically knowing how many moles are in the sample or what the pressure is. Since we don't know values for those, we can't use the ideal gas law to solve this, but we can pull this relationship out of it since we know the relationship between just volume and temperature by themselves, since we can isolate that effect from PV equals nRT. So now we just need to identify sort of what's time 1, what's time 2, what's before, what's after, however you want to think about it. And it doesn't really matter which one's which, as long as you get the pairings right. That we're told when the temperature is 298 Kelvin, the volume is 15 liters. So that's telling me if I'm saying that V1 is 15 liters, at that same point in time, the temperature was 298 Kelvin. So it doesn't matter if I call those 1 or 2, but they do have to be the same number. Then the other volume is what I don't know, is what I'm solving for, is what is the volume when the temperature is 200 Kelvin. So once we have all of this, we're just plugging into the relationship that we derived. V1, V2 is what we're solving for. So V2 will be V1 times T2 over T1, or 15 times 200 over 298, which is about 10.1 liters. Whatever, good enough, is about 10.1 liters or so. So the first thing we needed to do was identify what is the relationship between these two variables. They are directly related to one another. So V over T or T over V will work exactly the same way. So if you had done this where you moved V over here and N and R over here, that's also totally fine, and you'll come up with exactly the same answer. Once we've established this, we just set that expression equal to itself at 2 different points in time, and then identify our variables and plug things in. So let's look at another example. Cool, I can fit it all on the screen. Similar idea, under normal lab conditions, a balloon that occupies a volume of 1 liter contains 0.0409 moles of gas. Under these conditions, what is the volume of a balloon that contains 1 mole of gas? So we have different variables that are changing here, but we're going to go through exactly the same process. Start with the ideal gas law, figure out what is the relationship between those two variables, set up this type of relationship, plug things in, and solve. So take a few minutes and give that one a try on your own, and then we'll talk through it together. Alrighty, so we have slightly different things going on here in terms of what is changing. We are told that 1 liter of gas contains this number of moles under normal lab conditions, whatever that means. We weren't given specific temperature and pressure conditions, but that's fine, we don't need them. So we're asked under those same conditions, so constant temperature and pressure, what volume will a mole of gas occupy? So in this case, the things that are changing is the moles and the volume. Things that are staying constant are the temperature, the pressure, and, as always, R. So if we start from the ideal gas law, we are looking to get volume and moles onto the same side with our constants on the other side. Again, it doesn't matter which way you rearrange things, but we need to get V and N on the same side. One way to do that is to divide both sides by N. We need to get P out of there over on the other side with RT. So we can divide both sides by P. Again, if you did kind of the opposite and you ended up with the inverse of this, totally fine. You should get the same answer in the end. And since everything on the right here is constant, this is telling us that V divided by N is constant, or that V divided by N for some initial point in time will be equal to V divided by N for some second later point in time. And we can now pull out from our problem each of these variables. So we know that the volume of this balloon is 1 liter when there are 0.0409 moles of gas in that balloon. So that number of moles and that volume are at the same point of existence, the same point in time. What we are looking to determine is what will the volume be when there is 1 mole of gas in that balloon. So V2 is what we're looking to solve for here. So we can rearrange our equation, now or later, your choice. By multiplying both sides by N2, we solve for V2, which gets us this expression, and then we just need to plug in the values we were given. V1 was 1 liter, N2 was 1 mole, and N1 was 0.0409 moles, which gets us a volume of around 24.5 liters or so. So different variables, but same process. So we can start to see how the ideal gas law allows us to make relationships between any of these variables. As long as everything else is held constant, we're able to figure out how does moles affect volume, how does the previous one we did, how does temperature affect volume, so on and so forth. So there are technically some combinations of these that have special names. I am not interested in you knowing the names personally, but there's something that you may see at some point. So there's Boyle's law, which is the relationship between pressure and volume. P1 V1 equals P2 V2. There's Charles' law, which is the relationship between volume and temperature. V1 over T1 equals V2 over T2. There is Gay-Lussac's law, which is pressure and temperature. P1 over T1 equals P2 over T2. There's Avogadro's law, which is volume and moles. V1 over N1 equals V2 over N2. And last but not least, there is the combined gas law, which relates pressure, volume, and temperature. P1 V1 over T1 equals P2 V2 over T2. So again, I don't care. I'm not going to ask you about the names, but it's something that you see, so I figured I would at least mention it. All of these are just derived from the ideal gas law. But you will notice that this is not a complete list of all of the possible combinations of variables that you might be interested in. So there are other things. You should be able to derive any of these relationships from the ideal gas law, but these ones tend to come up more frequently, so they're named after the people who first discovered them for the most part, except for the combined gas law, not named after a person, just named because it is a combination of several gas laws. But I forget what else I was going to say. So I guess we're done.